So yesterday I talked about the FDF file and I ran a simulation, and simulation is for bulk silicon. It's just running. So what happened? Let me show you the results. So these are the so many files have been formed. So say this is the FDF file, and corresponding to this FDF file there is output file. So I started with the 4.5, right? So let us look at this out file, that what type of information it contains. That's more important. So let us have a look at the out file. VISI dot 045 dot out. So this is the output file, and it contains initially it contains information of this, and here it is the information that Siesta is running with NetCDF4 support on 8 nodes in parallel. 8 nodes in parallel. This is the pseudo potential information. Then there is a information of basis set. Right? If we go back to the last, in the last there is Q up minus Q down, or spin up minus spin down. It basically the charge difference of the up and the down spin, and its difference basically tells us about the magnetic moment. Right? So this is the magnetic moment. But silicon is not a magnetic material, but we have started with a different lattice constant. That's why it is saying that it has certain magnetic moment. If it is a relaxed structure, then it doesn't have any magnetic moment. Then this block contains test tensor. Then there is a block named total equal to, this is the total energy, and this is the Fermi energy. This is an electron volt. So this is the total energy. So what I will do, every output file contains total energy. I run the simulation for 0 CG step, right? Let me go back again. What is the command to go to the Naren? What is the command to go to the top of in VI editor? Shift plus G.
G.
Shift G.
देखो G.
2 times G.
अगर आपने टॉप पे जाना है तो G 2 टाइम, और एंड में जाना
Okay.
तो शिफ्ट.
ठीक. So I'm see here. It is CG step is 0. It is a force tolerance. So there are different out files, right? So what I will do, I will grab the total energy. I will grab the total energy from every out file, because so that means what I am doing, just try to understand this command, that what I am doing here. So it is grep. Grep means you are extracting certain line from the out file. So I told you the out file, and out file contains a single line containing total equal to sorry, equal to is not working here due to, okay, let me, yeah, equal to, and I am grabbing total equal to row from the out file. So there are so many out files. So I want to grab it from every line. So that means what I will do, star dot out. Then this vertical line, it is known as pipe, and space TEE. TEE means it will display it on the screen also. And I want to grab this data into some file. So let me give the name of the file. Whatever you want to give the name of the file, it's all up to you. So I am giving its name tenergy.dat. So what will happen, whatever information is contained in out file, that information grabbed from the out file and stored in the energy.dat file, right? That's what. Let us see energy.dat file is there or not. So this is the energy.dat file. So let me open this gedit energy.dat. So let me open it in energy.dat. You can delete rest of the information. So I am using it. I am deleting all this information using BI editor. So you can use it by you can delete this information using using a software gedit also, right? Right now I cannot tell you that how I am deleting it. You can delete it in gedit also, but right? So I grab the information and let us plot it. So this contains, a first column contains lattice constant, and this contains what we call total energy of the system, and let us try to plot it. I am using XMGrace energy.dat. So this is the plot. This is the plot which I am getting. Let me make it more bold. This is the total energy of the system. So this is the point around about 5.5. Yesterday I told you that 5.43 is the lattice constant. 5.43 is the lattice constant. So using this you will get this, means this is round about 5.5. It's a very good approximation to estimate the lattice constant. So this is the lattice constant of silicon, right? And let this simulation be finished. After that I will tell you how binding energy will be calculated, right? And now what I will do, the point at which minima will be occurred, I will use that. Let me go to again energy.dat. Say, yeah, 96. This is the value. 5.5 is the lattice constant. Even you can go up to the second or the third decimal place also, right? So what I did, lattice constant has been optimized. It was obtained. Now what I will do, I will take this as a main output file, and let us try to calculate now the band structure. Let us try to calculate now the band structure. So what I will do, I will make a directory another, say, let me call it as final, and go inside the final. I copied si.05.5.fdf to this file, and also copied this psf file start.psf to here. So it contains two files. Let me go to the again and let me rename it as si.fdf. So that means this is pisi.fdf. So what I am doing, let us go for the high symmetry points. These high symmetry points are not there. Ananya is there. Diamond के high symmetry points है पड़े हुए. Check it and send it to me. And let me talk about the high symmetry points. That what are the high symmetry points? Even you can also decide the high symmetry points also. For that, let us rerun siesta again, right? Let us rerun siesta underscore si.fdf t si dot out. And let me go to again utilities. There is a utility xp to xsf. I told you, I think yesterday or so. Let me go to there is util, and inside utils there is folder named contrib. Apostnico. Inside it there is a utility xp to xsf. So I told you that copy this xp to xsf into usr local bin. Given sudo command, you can do this one. bin, right? Is that clear now? So that's what you will do. And let us see whether simulation is over or not. Yeah, it's still running. So let it finish. So you copied it. And another very important software which you need to install, sudo apt get install xkrystal. This is a very good software. So you can install it also. Try to install it. Have you installed xkrystal? So what we will do, we will try to visualize the output file in xkrystal. And there is another utility, let me talk about that also. There is another utility, bands. Inside the bands, there are two executable files. One is the EIG FAT to plot. It's the FAT band analysis. So here GNU bands is the utility which is used to plot the extract the band file so that you are able to plot it. because every file which was generated, it cannot be directly plotted, so you need to modify the file. So GNU bands is a utility which will format your band's information so that it can be plotted, and EIG FAT to plot is a partial band analysis tool. Say which orbital is how much is contributing. The thickness of the band tells you that how much contribution every band is giving to where and where, right? So, but here I am not talking about the EIG FAT to plot, but I simply tell you that GNU bands utility, right?
गोल्ड का है गोल्ड का ही है नहीं सिलिकॉन का है
Let me see, yeah, it's almost finished, and it is the Fermi energy 5.39, 5.39. Job is completed. Okay, so say bands file is not formed there, still band file is not formed, but what you will do, because we need to know that what are the high symmetry points. This is a very important point in any DFT code. In any DFT code, not in CS star. Right? So XB to XSF, I basically convert this utility. So I just given a command XB to XSF, enter. It says that system level means it requires this name only. Be very much sure. So it is SI, and just enter, found and open. So if I look at it, earlier it is XV file is there, now there is a XSF file is there. XSF file is there. So now I will open XCRISDON. It's a XSF file, to dash XSF, then SI dot XSF. This is a way to open a XSF file. Open a XSF file. Say, it is the structure of silicon. This is the structure of silicon. Have a look at it. You can repeat it also. In primitive mode it should be like this. In this mode it looks like this. So even you can repeat it. See, this is the structure of this. Even you can measure the bond length and bond angles also. Even you can measure bond length and bond angles. You go to here. Distances, if you want to measure the distance between these two, it was done to 3.8891. I'm just approximating. Then even you can also measure the angles also. So say this is the angle between, sorry, go to the, close it and then angle, say this is the angle between these two. So it is a 60 degree. Right? This is a way. And then there is a very important tool. But before moving towards that tool, what I will do, let me talk about say these are the high symmetry points. This is for the triclinic, primitive, monoclinic, rhombohedral, orthorhombic, FCC, orthorhombic, and so on. Hexagonal, cubic. So our structure is this one. और इसके जो हाई सिमेट्री पॉइंट्स आते हैं वो कौन कौन से हैं, और इसकी थोड़ी सी यहाँ पे इंफॉर्मेशन भी आपको मिल जाएगी। से BCC, हेक्सागोनल, FCC, and then description. So gamma is what? Gamma is the center of Brillouin zone. So if you don't know the high symmetry points, this is a very important point. If you don't know that what are the high symmetry points, then what will you do? You go to here, tools, go to the tools and K path selection, and this is the Brillouin zone corresponding to your Rio structure. It is in the reciprocal space. And let me show you the high symmetry points now, which we have taken. Yeah, it's there in it. This is the block which I have used. It's gamma. So the point is basically gamma point is there with us. One point is gamma point, another is K, L, U, W and gamma. So how to choose these points? Let me tell you those points. Right? This is a one way. Another way, if you go to the database, you will get these high symmetry points. But for new structures whose gamma high symmetry points are not known to you, structure will be different, then you have to determine. Because when you have to switch over from 3D to 2D or 1D, then gamma points must change. So you know that how those gamma points can be taken. So say this is the gamma, it is the center. These are the coordinates. So its leveling will be gamma. So let us represent it by G. After this, another is the K, which I have taken. So what is K? For FCC, K is the middle of an edge joining two hexagonal faces. Middle of an edge joining two hexagonal faces. So this is the K point. We have two hexagonal faces. So let me go to the here. And these are the two hexagonal faces. So it is the point. This point is K. You can take this point, or because it gives a negative, then you can take also this point. Yeah, this is either this way, or you can even so you can take this also. So this point is K. This is a way that how will you choose a K high symmetry points. Similarly, L is what? Let me go to the L. L is the center of hexagonal face. L is the center of, I am talking about for FCC. So L is the center of hexagonal face. So how will you decide that? Sorry. Yeah, it's there. Center of hexagonal face means you are talking about this point. This is the center of hexagonal face. Similarly, you can go for U and W and gamma. So I am now directly using these high symmetry points which are already with me, and there are some additional flags are also there to do band structure calculations. So for that, what will you do? I just go to here. I just copied this block. Right, and then I put it back in the, because this is our final calculation, so I am again opening a new tab. So BISI dot FDF, I am just opening it. So here is the band structure information. Yeah. So this is band structure. Band, line, scale, reciprocal lattice vector, that's what I am using here. right? So this is the information of high symmetry points. Means 1 to 50 means from gamma to k you are taking 50 data points, and then again 50 from k to l, then again l to you are taking 50 points, and so on. And this is the block which you are taking. Now I will again run the simulation. I'm just coming out of this. So this is a way that how do we choose the high symmetry points. This is a very important point. You must know, because there is a one advantage of CS star, that you can switch the dimensionality. You can switch from 3D to 2D, 2D to 1D and the 0D. So you must be very particular about that, how to choose the high symmetry points. If high symmetry points are not according to your structure, then your band structure will never be good. It gives you band structure, but that may not be a band structure which is good for, that may be wrong. So I am again running CS star here. Yeah. Actually, when you move from 3D to 2D or 2D to 1D, the direction, actually we are now in the reciprocal space. So when you take the reciprocal of something, when you take the reciprocal of large lattice constant, then reciprocal will be less. When you take the reciprocal of small, it will be large. So when you take a say vacuum along z-axis, so then there is no need to take the high symmetry points along the z part, because along z it is a it's a minima. Yeah. Yeah, x and y, and z it will be 0. It should be in that way, but it depends upon structure to structure part. But actually this is a way to look at the let me see if I have got some time, then I will tell you. Otherwise, when you design some 2D material, I'll let you know online mode also, right? So it is LS, yeah, because that will require more time and to think. Yeah. Right now on my laptop is not there, because I don't keep any data with me. This is all data with my students. Yeah. So see, now there is another utility. I told you that there is a utility GNU band. So you copied that GNU band's utility from there to the USR local pin. So I will use that utility GNU bands, because there is a bands file. I want to convert its information. So GNU bands. SI dot bands T, say bands dot dat. So I converted it into another format. So this is bands dot dat. It has been converted, right? So XM Grace, you can plot now the bands dot dat. This is the bands dot dat has been plotted, and you can shift the Fermi energy. Narendra, what is the command to shift the Fermi energy in GNU bands? Minus F, capital or small? Capital, okay. Just check it out. I am just doing it. GNU bands dash F, right? So it automatically shifts the Fermi energy to 0 level. So now let me plot this XM Grace bands dot dat. I want to see the things near the Fermi energy. So for that, what I will do, I make changes in the axis. So it is x-axis is from here to roughly it is it is 2.45. It is 2.45, and along y-axis say it is minus 5 to 5. So this is the band structure of silicon. And you will get the information of high symmetry points also. Let me show you that, and let me make it darker. So this is the band structure of silicon. At the lattice constant to 5.5. It is not exact value. You have to fine tune things in up to 2 or 3 decimal places. Then you will get the actual lattice constant. It's just a rough calculation. And similarly, there is another utility, FMP DOS. In the folder of Aposnikov in the utils, using that you can extract density of state information also. Right? You can extract the information of density of state also from that. I have shown that in my video lectures also. Because right now I want to tell you how dimensionality will change. I also told that, but now I will again reconnect the things, that how things will change and how reciprocal space will also be changed accordingly. So I told you the band structure, and FMP DOS utility, I made some video on that also, and these are available on YouTube. So that's what I did here, and another thing, yeah. So let me change let me show you one more examples which I already did. So let me go to the, I think test directory is there. Yeah, I made some system, yeah, H2O. This is a simulation I run for the carbon dioxide molecule. I have taken it as a linear molecule. I have taken input as a linear molecule, but after optimization it was like this. And this movie I made with the help of X crystal. Is it available on YouTube? Yeah, it's also available. I told them that how molecule will be designed. So it will take care. And another very important thing which I want to share with you, if I look at its out file, its out file is here. Yeah, it is the out file. If I look at the out file, then it shows that what type of system is this one. Say SYSTEM system type. Yeah, it shows it's a molecule. It shows that it's a molecule. In the out file, every information is written. If it is two-dimensional material, then it says that it's a slab. But if I go to after running in the out file, yeah, yeah, depending upon how its lattice constant. And another very interesting thing, if you are running a molecule or cluster, nano cluster, there is no need to give lattice vectors. You simply put atoms in the coordinates for actual coordinates format, and it will recognize it as it will automatically take care of everything. Huh? Nano structures means nanoparticles. If we are running some calculation for nanoparticles, molecules, then there is no need to give information regarding lattice constant and the lattice vector. You simply put coordinates. Let me see its FDF file. Say, I have not given any information regarding this here. Okay. This is the FDF file of this. Number of species, two types of species. One is the carbon and another is the oxygen. And this structure is linear. Initially, the structure is linear, but after optimization, it gives us a band structure. No additional flags. So it will take care of everything. But if you want to do calculation with cell, then that is large enough so that they do not interact with each other, as I told you in the earlier lectures also. Yes? Yeah. For bulk, you have to take the high symmetry points as, let me show you that also. BISI dot FDF. Let me come to this point also. This is a very important point. When you are switching over from 3 dimension to 1 dimension, 2 dimension, and say vacuum is along, in the morning lecture I told you that, right? So say vacuum is along x-axis. So that means the dimension of that x is very large. So for that, need not to take large number of k points. So for that, say if vacuum is along x-axis, let me show you. Say if for 3D, K mesh is 1500, I am talking about K mesh. 0, 15, 0, 0, 0, 15. But now I am saying that I am switching over from 3D to 2D, and let us assume that along x-axis there is a vacuum. Then that means reciprocal space along x-axis is a very small. There is no need to take a larger mesh for integration. Basically, these K mesh means you are integrating in the reciprocal space. If I recall the integration means you have to take a mesh and then you will integrate numerically. Same idea I am using here. So that means along x-axis, vacuum means large lattice constant. So large lattice constant is there, then there is no need to take large number of k points. So for that you will take 1, 0, 0, 0, 15, 0, 0, 0 and 15. This has a k mesh for 3D. But when you are switching from 2D to 1D, so for 1D, let us assume that x and y in those directions we are taking vacuum. So if these two directions contains vacuum, that means what? That means your K mesh will be 1, 0, 0, 0, 1, 0, 0, 0, 15. And in quantum espresso you will take 15, 15, 15. In quantum espresso, block is like this. In siesta, block is like this. Idea will remain the same. It will not change. Whatever code you are using. but you must know that how things are changing from when you are switching over the dimensionality. Just a minute. But when you do it for the zero dimensional, for zero dimensional it is 1 1 1. If you increase the K mesh, then if you increase the K mesh, that means very large computational cost will be required. And if you say, if you are doing some calculation with the supercell, say, and you are doing some doping, let me answer that question. This is a very important question. Yeah. Say, if I look at the two-dimensional cell, graphene structure is like this. What I want to do some doping, so that means I repeated this, say, cell 8 by 8. That means I am increasing the real space 8 by 8 and then make some doping. Then there is no need to take, say, if for this small structure, means from the primitive graphene structure you are taking, say, 115 and 15 as a K mesh. But if you are repeating now this as 8 by 8 cell, then your K mesh can be decreased. You can use it as like this 0 5 0 0 5, because you have increased its size also. Now you are not taking this cell, but you are taking a large number of cell and then making doping. If you take again 15 15, then computation cost will go very high. There is no need to do that. No, not 1 1 1. 1 is only along the direction in which you are taking a vacuum. So this is a very important point, because people are interested in using doping, adsorption and the absorption like that. Then for that you have to keep in mind these things. Otherwise computational cost will go very high. Basically, actually what happens, people will also use sometimes 30 by 30 by 30 block also. But in general, if you are repeating it, say, 4 times, then you can divide it by 4 times. But if you take a little bit larger K mesh, then it will do better integration and gives you better band structure. You can learn this by, but this is a very important point. So I think I had touched different aspects of this, and I will share with you few files also. I give this work to one of my student, and he will share with you on WhatsApp group also. But you get all these lectures, small lectures on YouTube also. So with this, not thank, but there is some another thing which I want to share with you. This is another simulation which was running. Let me go to it. Yeah, I have run this calculation. It's 4, 8, 9, 10 and 11. Let me grab again total equal to star dot out t energy dot dat gedit energy dot h si dot replace all dot out c star, yeah, and then total and grace energy dot dat. This is a very important point which I want to share with you. देखिए क्या हो रहा है इसमें, बाइंडिंग एनर्जी की मैं बात करूं, जैसे जैसे लैटिस कांस्टेंट बढ़ता जाएगा वैसे वैसे क्या होगा, जैसे जैसे लैटिस कांस्टेंट बढ़ेगा ये वैल्यू इस तरह से 15-20 के आसपास इट गोज लाइक दिस, कांस्टेंट आ जाएगा. So that means now, because what I am doing, I am increasing the lattice constant in small steps, and interaction between those two atoms will almost become negligible. So that means that will now become a what? That will become a isolated atoms. Two different isolated atoms मेरे पास बन जाएंगे. So isolate करने के लिए जितनी एनर्जी की जरूरत होती है, what we call that as the binding energy or the coercive energy. तो इस तरह से मेरे पास binding energy आ जाएगी. This is a way to look at it. Energy क्या करेगी? It converges to a single value. इसलिए मैंने 15 minute, but that simulation will take a more time. So we must have certain type of feeling of the definition which we have learnt. Now that those two atoms now starts behaving like a isolated atoms, right? So I think that's all from my side. जितना मुझे टाइम मिला मैंने कोशिश की आपको पूरा बताने की. So मैं चाहता हूँ कि आप लोग अच्छा काम करें सभी के सभी रिसर्च में. So I thank you all.